we're looking at the concept of fixed pulley. So let's look at fixed pulley. And first thing is, why is it fixed? I mean, what is fixed about fixed pulley? Well, we know pulley. So this is the circle. And this is yeah, this is your circle, and this is where you are able to attach and fix this to a roof which is stationary. And thus making it as a fixed pulley. Okay, so this is a fixed pulley. Because this part is fixed. Okay, yes, that's why it's a fixed pulley. Now, what does it function? What is the function of this? And how do we use this basically? So basically, let me extend this. So we are standing over here. And a bit closer actually. And you are pulling the rope downwards. So this is your load and this is your effort. Okay, quite simple. I am pulling this down. What will happen to the load? Yes, it will move up. How is that possible? I mean, I'm pulling it down. This is moving up. Well, because of the pulley. And so we have a key point about pulley, that is, it is able to redirect force. Pulley changes the direction of applied force, similar to lever. So there is some similarity with lever. So we'll have a look at that also. So load is nothing but things that we are trying to lift. And effort is, well, self-explanatory. I don't want to go to that. So we have a point about pulley being a pulley as a lever, not lever. So for that, let me draw a lever. And then you have your fulcrum. You put your load over here. Sorry, not load, sorry. You put your effort over here, for example. And you'll get to see the output or your load over here moving up. Do you guys agree? Now imagine this. Imagine a circle. Oh, that. Not that. Something like this. Imagine circle like this. Right? And what is this? That becomes your pulley. That's it. So it's doing the same job. Can you see that? It's one side, it's moving the rope up. Another side, it is getting the rope down. So here too, it's the same thing. And that's why we can talk of pulley as a functioning as a lever. Okay. Next, the next perspective is with tension. This comes from the first point. Tension along the rope. I hope you guys have written this. So I'm talking about the first point. Where is that? Where is this? If the rope is massless, the tension is the same at both the ends. That is, if I'm able to attach a load and able to attach a rope, and at this end, if we happen to pull with a force of 10 Newton, at this end, you will get to see 10 Newton of pull, provided this is massless. Okay, so this is the funda. This you guys agree, right? So that's how a rope can behave. Now imagine you take the same rope and you attach it or take it across a pulley. So to you guys, if my effort is 10 Newton, how much will the load at the load end, how much force will we see? Yes, we will see 10 Newton of pull. Do you guys agree? It's commonsensical when you see it from the perspective of tension. From this, just that this entire length has been put across the pulley, right? Basically, we are shifting that from here to here. Okay, I'm going very slow. So because it's the first time you guys will be seeing this. Now, in terms of length, view in terms of, now it will get interesting, guys. If it's already interesting, good. If not, now it will get interesting. A bit more interesting. So can I use this? I kind of can. Say this is before and after scenario, basically. Okay, let me put it this way. Say you have your effort over here, load over here. I'll make it a bit dramatic. Okay, perfect. Say you have a load over here. And you have effort over here. I'll just represent that with a small, a bit shaded in this manner. That's your load. Now, to your effort's height, the load moves, and to your load height, the effort moves. So basically, I'm going to make this effort move here. What will happen to the load is the question. So this is my effort. And if I make the effort move to this height, what will happen to the load? And this comes from this particular concept. Length of the rope is fixed. So if here the length get displaced by some amount of, say, h. If this is 10 centimeter, if the effort moves by 10 centimeter, what will happen to the load? The load will move up by 10 centimeter, as simple as that. Okay, so this is displaced by 10 centimeter, and this 2 is displaced by 10 centimeter. So this is 1 and this is 2. So this is before and after scenario. Before and after scenarios. Okay. So from here, this measurements and this conversation, we will take it to a new topic called as length ratio. Officially, it's not there, but this is something that I am making up so that the conversation will make more sense as and when we go. Sorry, that thing, oh no, that won't go away. That's a glitch, guys. Please don't mind this. This will not go away. I'm not going to erase this. So length ratio has to do with the displacement at the effort end divided by displacement at the load end. It's just a ratio. Effort and the displacement is, in this case, 10 centimeter, or let me call it as h divided by h. Right? If, yeah, you please ignore this. Ignore the direction. So if I come down by h, at the load end, it will move up by h because the length can't change. So the ratio is 1. Agree? So length ratio is 1. Next, we'll define it as, we'll define velocity ratio. Velocity ratio is actually this, but I'm going to take it forward as, it'll come out to be this, but let me put it in this way. So again, velocity at the effort by velocity at the load, right? Only magnitude is what you're looking at. So this is nothing but displacement at the effort by time divided by displacement. I don't know why am I writing that. Anyways, I'm calling this as displacement. Displacement at the load by time. So time gets cancelled. We have the same ratio and this 2 is equal to 1. So imagine if the effort is moving at 10 kilometers per hour downward direction, load will also be moving at 10 kilometers per hour but in upward direction. Does it make sense? All this commonsensical. If you feel that this is easy, good, because connecting to this is all your numericals and everything. So pulley is also simple, provided you understand the fundamentals. And yeah. Next we have acceleration ratio. Does it make sense? We saw displacement or length ratio. Then we saw your velocity ratio, and now you're looking at acceleration ratio. So what is acceleration ratio? What do you think it would be? Yes, this 2 is nothing but change in velocity at the effort divided by change in velocity at the load. And this is nothing but, all of this will lead to 1. Because the rate at which the velocity is changing, if it's changing, it will be equal to that of the load because the length are changing that way. These are physical things. This you can't do much. And from all of this, we have something called as force ratio. Okay. So this too is, guys, something that I'm making up. So this is nothing but the effort by something called as load. This is nothing but your force at the effort divided by force at the load. So from here we have something called as mechanical. This is an actual advantage. When it comes to pulley, this is the actual stuff. So this is to do with mechanical advantage, has to do with force at the load by the effort. Load and effort are synonym to our force being applied or seen at the ends. So this is the force applied and this is the force seen at the load end. Okay, this is the force at the effort end And this is the force that we see at the load end. Okay, so that's your mechanical advantage. So they are inversely proportional to each other. So this is me made up. Let me put it this way. This is official. This is not official. Again, this helps us actually. That's all, nothing else. So we have, this is also not official. Why am I doing this way is you get a better sense of what exactly happens. As in when we move forward, you will understand. And it's easier to connect this way, you know. First I started with length, then velocity, then acceleration, and then force. And then something called as mechanical advantage, which is a reciprocal of force ratio. So not official, not official. This is official. And this is not official. So you need to know that. By chance, if you guys don't get any one of these definitions out there, because I just made it up. Okay, so sorry, I think I made this all slow. So let me kind of wind it up faster. What we are looking at is a type of pulley called as fixed pulley. And the definition is that the pulley that is attached to a stationary structure that does not move. Of course, stationary means and does not move. So it's fixed to stationary, so obviously it will not move. So from length, we can derive the idea of velocity ratio. So in this case, the velocity ratio is 1. Reason being, if a person pulls 10 centimeter, the other end, the rope gets displaced by 10 centimeter and thus the load is moved up by 10 centimeter or moved down by 10 centimeter. Non-official definition, acceleration ratio is nothing but the acceleration we see at load and effort end. So if you guys are thinking all of this is 1 all the time, well, it's not. That's what we'll see in the next video. So force ratio, the effort force is equal to the load force in this case. So this results in the ratio being 1. Okay. So and the write up, this is must for you guys to write. So nothing much from here. Okay. So you guys can write this and pretty much copy from everything from here and you're done. Oh yeah, let me revise this also. So load is something which we are pulling up. Effort is the point you are pulling from. Pulley can be viewed as a lever. It helps. So it as lever can redirect force. Yes. So the pulley also can. So when we talk about tension along the rope, right? So if I put one value over here, the same value is over here as well. So in terms of view in terms of not load actually, sorry, length. I told length, but I wrote load. In terms of length, the effort moves by 10 centimeter, the load will move up by 10 centimeter. So the amount of displacement will be fixed. So say this is X meters. This is the scenario. So from here, I'll be defining something called as length ratio. It's nothing but how much the effort has got displaced compared to the load. Velocity ratio is how much the velocity of the effort is seen compared to that of the how much velocity is seen at the load end. And acceleration, similar thing. And finally, officially, we have something called as mechanical advantage. That is the load, how much force we get to see at the load compared to that of the force seen at the effort. Again, all of this will make more sense when we go on to the next type of pulley.